Okay, so we're trying to find for question 5 point P, which is the foot of the perpendicular from the point A to the line. So we want these coordinates. Now we know for a particular lambda that P has the coordinates of the form 1, 2, 5 plus lambda lots of 1, 1, 0 because it lies on this line. And the way we're going to do this is we're going to work out a vector A to P. We know it's perpendicular to the vector 1, 1, 0, so when we dot them together we should get 0. So to work out the vector A to P then, we know that's the position vector of P, take away the position vector of A, so that's 1, 2, 5. So that's 1, 2, 5 plus lambda lots of 1, 1, 0. Take away the point A, which is 6 minus 1, 5. Okay, working that out, A to P would be 1 minus 6 minus 5 plus lambda, 3 plus lambda, and 0. So that's an expression for this vector here joining A to P, and then if they're perpendicular, then when I dot that with the vector direction of the line 1, 1, 0, I should get 0. So if we do that, we've got minus 5 plus lambda plus 3 plus lambda equals 0. So minus 5 plus 3 is minus 2 plus 2 lambda, 0. And that means lambda's going to be 1. So if I substitute lambda as 1 back into this point now, I would have 1 plus lambda lots of 1, more commonly known as 2. 2 plus 1 is 3, 5 plus nothing is 5, and so I've got the coordinates of the point P there. Okay, I'm going to keep using this diagram, so if I get rid of this little bit of working to help us out a little bit. So if this is a mirror line and we're reflecting the point A in this line, because this is perpendicular, the reflection is going to come out perpendicular as well. And also the distance, if it's a reflection from A to P, is going to be the same as the distance from P onwards. So if we could work out to the reflection point B, if we could work out this vector, if we did it again from P, we would work out the coordinates of B. So to get from A to P then, now we know the number coordinates. To get from A to P, you go minus 4, 4, 0. So that gets us from A to P. So now if we start off with the position vector of P and add that on, we should get to this point B. Means the coordinates of the point B are minus 2, 7, and 5. Okay, let's get rid of all this working and have a look at part C. Okay, so the point C is going to So the point C is lying along this line, so it's either going to be here or here, so that this triangle or this triangle are equilateral. And we're going to use some of our points about equilateral triangles to find the possible coordinates of the point C. So the main thing we're going to use here is that we know or could work out the length of the line from A to B using Pythagoras. And then if I set up a general coordinate for the point C again, so that's 1, 2, 5 plus lambda lots of 1, 1, 1, 0. If I work out the distance from this line from B to C, it's going to be the same as distance from A to B, and I'm imagining I'm going to get some sort of quadratic, so I could get the coordinates of the alternative point C there. So let's do that. So first of all, distance from A to B then. So we knew to get from A to P was the vector 440. So A to B was double that, which was 880. Working out the length of that line, just using Pythagoras' root 64 plus 64, which is root 128. So we know the length of our sides of our equilateral triangle. So now I'm going to get an expression of the line joining A to C, which we already did earlier, because when we were taking P as a general point of the line, we did P take away A. C has the same general equation for some different lambda, so we're going to do C take away A. So using what we did earlier, the vector AC would be minus 5 plus lambda, 3 plus lambda, and 0. If you don't follow what I just did, all you're doing is C take away A to get A to C. And you can just work that out again. Okay, so the length of the line A to C then, if we do Pythagoras on that, actually I'm going to look at the square of it to save me square rooting and having nasty square root signs. Looking at the length of the line, it would be minus 5 plus lambda squared plus 3 plus lambda squared. Just doing Pythagoras on there to find the modulus. And don't use square root because I've written the modulus squared. So that gives me 25 minus 10 lambda plus lambda squared plus 9 plus 6 lambda plus lambda squared. So that's 2 lambda squared minus 4 lambda plus 34. That's really horrible to solve. So we knew we made you buy these silver calculators for good reason. Let's just find the answer to that online. Sorry, I've just set that equal to 0 instead of 128. So that was an expression for the length of the line squared, and I need to put it equal to this squared, so that's 128, because all the sides of the triangle, if they're each equilateral, are the same. So I've got lambda squared minus 2, so that would be half of that, should be 64, minus 2 lambda minus 47. So putting that in your calculator comes out to be lambda is 1 plus or minus 4 root 3. Okay. So I need to sub in the two different values for lambda to get the coordinates there. So if lambda is 1 plus 4 root 3, then the coordinate of C is going to be 1 plus 1 lot of this will be 2 plus 4 root 3. The y1 would be 3 plus 4 root 3. And the z1 is still going to be 5. And then if lambda is 1 minus 4 root 3, that's just going to change these to negatives. And we're finished.